Write down the time, 3:41. I wanted to turn on the chat and, oh, there it goes. Oh, I see what I'm doing. Try this again. Let's turn on the chat, then go full screen. I like that layout better. Okay. All right. So, all right, I'm going to kind of read this here. And then, as you said, can you do it analytically? Absolutely. And so I'm going to give that a try here. Let's call this, for anybody who might be tuning into the video recording, block connected to string over a pulley or something like that, connected to a string over a pulley. That would be probably clear enough here. All right. And so I'm going to go ahead and say, and maybe draw the picture here. So they've got this incline, and you have a block on the incline. And this is block number 2, mass 2, because it says here block number 1 with a mass of, so I'm going to string up here that goes over some kind of pulley. And put number 2. So, no, that's number 1. Okay, so block number 1 with a mass of 2.9 kilograms is connected by a string over a pulley to block number 2, which is on a frictionless incline of 20 degrees. In order for block number 2 to slide down the incline, it must have a minimum mass of, and so that's the problem. We're trying to look for the mass. And then, of course, it's kind of an active figure. It says, click on the image below, a helpful interaction. Okay, so to do this one analytically, let's do the following. And like I said, there were kind of 2 options. And I'll do the one that I think conceptually is easier, but mathematically harder. And then we'll maybe flip to the one that's maybe a little easier mathematically. Notice I only said easier, a little easier. But maybe conceptually is a little more challenging. But I'm going to just kind of divide into 2 columns and do a free body diagram of each of them. Now, block number 1 would look something like this. Okay. And, I don't know if I've ever said it this semester, so I'm going to say it now. I know in some other the videos recordings I put out, you might have heard me say it if you listen to them, that I like to think of these as 4 steps. The first step 1, is you got a good physical picture of what's going on. And so I'd say in this case, my physical picture is I've got competing forces, if you will. Block 1 is trying to go down and move everything, which would turn the pulley in a clockwise direction. But block number 2 is trying to go down the incline, which of course would pull block number 1 up and make it go in a counterclockwise direction. So that's our competing forces here. And so if block number 1 is above a certain mass, and that's the, kind of the question here, in order for block number 2 to slide down the incline, it must have so much mass. So you start making this having a lot of mass, it will overcome number 1 and lift it up. On the other hand, it can go the other direction if block number 1 is more than number 2. Okay. So, and I don't mean more, but more by a certain amount, because this incline has a significant play on it. So anyways, there is what I call step number 1. You got a good physical picture of what's going to go on here, because number 2 is a free body diagram. So in this case, block number 1 is being pulled down by M1G and being lifted up by a tension T. And so there's some kind of stress, some kind of tension in this cord here. Okay. Now, block number 2 is a little more complicated free body diagram. In fact, maybe I should actually draw it tilted. Maybe that's a little too much tilt. It's only supposed to be 20 degrees. But as I draw the forces on block number 2, there would be gravity pulling it straight down, M2G. And that's the one we need to talk a little bit about. There would also be the contact between the block and the incline. So that would be a normal force. And then, of course, the other thing touching it is the tension T. And so those would be the 3 forces on block number 2. So it looks like we've got 2 forces on block number 1 and 3 forces on block number 2. That's what I call step number 2 free body diagram. Because if you do that one well, and I must say it's hard to do step number 2 well unless you did step number 1. So step number 1, you got to get that physical picture. And if you do that well, that leads to step number 2. And if you do that well, that actually leads to step number 3, which I call writing out the equations. And then solving the equation is step number 4. And of course, if you've done number 3 well, the 4 follows. And so hopefully each of these steps is a little bit easier, but overall, the 4 steps, can seem overwhelming in one big step. So kind of break this down into these little steps. And that's why we do the free body diagrams. And so I think that's what is hopefully being emphasized to you, that these free body diagrams are a way to kind of take a complicated problem and look at just the object. Now, in this case, I'm looking at objects. It's plural because there's 2 of them. And so that makes it a little harder than some of the other problems, because we got 2 things going on. That's why I say there is a second way of doing this problem that you might like, because we can kind of look at this as one big object. And conceptually, that might be a little weird. But then mathematically, it's going to be a little easier because we only have to apply our math to one object instead of 2 objects. So that's kind of just a little foreshadowing of what we'll do next in this problem. But conceptually, I think it's easier to think of them as 2 separate objects, even though that's going to lead to a little harder mathematics. Okay, so thinking of them as 2 separate objects, I've drawn the free body diagram. Let me call this page 1, because continuing in this scheme, I hope I don't narrow my paper too much so I can write out these equations. If I look at this block 1, and so now I'm going on to step number 3, let's write out these equations. I can say, all right, what's going on? And this brings us back to step number 1. And we said that one of 2 things are going to happen. Either block 1 is going to be so heavy it goes downward, or block 2 is so heavy that even though it's on an incline, it lifts block number 1 up. So I need to make a grid so I can write out my equation. And my strong recommendation is to always put one of your axes, it doesn't matter which one, but one of them in the direction it will accelerate. Now, if you know that, I got to admit, some problems we don't know that. But for this problem, I think we do. This problem, we know it either goes up or down. Okay, and so I'm going to put my axes, which traditionally is the y-axis, but let's talk about that for a moment too. But traditionally it's the y-axis. I'm going to make it go up and down.
In this scenario with 2 different tilts, does the axis have to be the same?
Right. No. And see that. Okay. So this is what you're getting at. This is what's going to make it maybe a little bit harder thinking of a separate object, but I would do this then. For my second object, I would tilt it so that one axis is along the direction it moves. And of course, the other one would be perpendicular to that. And so I like to say that maybe for this problem, and ones like it, don't use the traditional horizontal and vertical axes. You'll make the math a lot easier if you make one of your axes along the direction of the acceleration. So that's the advice I always like to give students. Yeah. And I also want to emphasize, you don't have to do that. But when we start diving into the math, I will tell you that and show you why this will make it mathematically easy. So again, if you know the direction it's going to move, which for both blocks we do, set up the axes. And let me give you another, I think, helpful advice is make them the same axis. Don't call this one Y and this one X. See, my default is to call this one Y. And my default is to call this one X. But now I got an object moving in Y coupled to an object that moves in X. Now, again, nothing wrong with that. But I think it's just a little bit easier to say, when this moves X, this moves X. So here I have kind of a choice to make, because traditionally, I like to call this Y and this X. And if I only rotate it, I guess my default would be call this one the X. So it again, doesn't matter which way you want to go with it. And again, you don't have to, but I would suggest, why don't we do this? Why don't we call this angled one the X-axis? And because of that, this up and down one the X-axis. And so I'll just turn back to you. Are gonna be okay?
Yeah, that makes sense.
Okay. Because I'll call them Y if you want, but now I have another decision to make. Which way do we want to call positive? You see, traditionally, we call up positive. Okay. But if this block 1 goes up, that means block 2 goes down. So again, don't have to, but I don't want to be worried about the mathematics of when this one moves positive, this one moves negative. So I'm going to do this. I'm going to call up the positive X-axis. And then I'm going to call down the incline the positive X-axis. Which means that the other direction is the Y-axis. And kind of over here, if you kind of imagine taking the tradition, then this over here, I guess, would be the positive Y-axis. So I have a kind of non-traditional axis that because it's non-traditional, may be a little bothersome at first. But I'm hoping to convince you that it's worth your time and effort to say, why don't we make motion positive and X for one be the same as the other? And it doesn't matter what you pick. So we could have picked up as positive Y. I would just suggest that we call them down positive. We could have called down a positive X on block number 1. And so if you do that, I would suggest you call up the hill a positive X. So the advantage is positives go with positives and X's go with X's. Because we're dealing with two objects. And if we don't do that, we end up making extra connections of mathematics and we make it looking extra hard. Okay, so I'll say it again. I think you will come up with easiest problems if you do these three things. One, you make one of the axes the direction it moves. Two, you make x's go with x's for the two objects. And three, you make them both either positive or both negative. You make the same sign. Okay, so if you follow those three things, your equations will be a lot easier. Even if it will be kind of non-traditional. I mean, going up, calling that x, that's non-traditional. And if angle down, x, that's non-traditional. In fact, it's going down and we're calling that positive. So, all right, so if we can get over the non-traditional, we'll see a huge advantage. Okay, so with that in mind, now let me write out my equations, because I would say I'm going to kind of divide my second page here into 4 areas. This first one will be block 1, and this will be the x part of block 1, and this will be the y part of block 1. Down here, I'm going to do block 2, and I'll do x motion for block 2 and y motion for block 2. Now, it turns out, and it's probably not quite so obvious yet, but the y motion of each of these are not going to be used. I'll say that because block number one doesn't do anything in the y direction. And if you come back to our free body diagram, sure, there are some forces in the y direction, but those forces don't really depend on anything in the x direction, unless there was friction. Now if there's friction, remember, friction in the x direction depends on normal force in the y direction. Oh, have you guys got that far? You got the friction, right? Yeah.
Yeah.
Okay. So had this not been, see, they say it is a frictionless incline. We're going to see that what we do for the y direction is irrelevant. But you never know that at first. So again, this step 3, I'm trying to say, is just write out the equation. But before I can do step 3, I have to make a grid. And that's why I say making a grid that has these 3 principles. One of the axes is the direction it accelerates. 2, the x's or the same axis goes with each other. So x's with x's and y's with y's. And then pluses with pluses and minus with minus. All right, so keeping this free body diagram in mind, I'll keep it kind of on the screen. So here's block 1. Let me write out the equations in the x direction. So in the x direction, I have a tension going up, so plus T, and I have a weight going down, so minus M1G. Maybe I'll put before it, I should have said add up the forces in the x direction, because we're going to set that equal to MA in the x direction. So that's what I'm working when I say step 3, write out the equation. When I say write out the equations, I really mean apply Newton's second law. All right, so these are the 2 forces in the x direction, and that has to equal its mass, so that would be M1 times the acceleration in the, and here's where I'm going to pause. Here's where we see the advantage of having all the acceleration in the x direction, because technically Newton's second law said if you add up the forces in the x direction, you get the acceleration in the x direction. But because I put all of the acceleration in the x direction, I'm just going to say the acceleration in the x direction is everything. It's just A. There is no A cosine or A sine of it. That's why I was saying this will make this equation easier. Now watch the y direction. In the y direction, it's the same logic. The sum of the forces in the y direction have to equal mass times acceleration in the y direction. And again, if you set up the motion along one of the axes to be A, then the other one has no acceleration. It doesn't move in that direction. So again, not only is there not a sine or a cosine to worry about, there's not even a number to worry about. And those equations are easier. So I'll say it again. That's why I kept saying, set up your axes in the direction it accelerates, because the AX just becomes A and AY just becomes 0. And those are easier equations than things that have A sine theta and A cosine theta. So you see that. Now, if you look at the forces in the y direction from block number 1, they're boring. There aren't any of them. I guess technically this is right. 0 equals 0. But this is the part I was saying, it's not going to do us any good. But hey, some problems we need that. So it's probably good to see it. All right. So we don't have that. That goes away. And see, like I said, if we didn't have this being 0 here, we had some tilt to it, we might have something like 4 equations and 4 unknowns. Much nicer if we don't. Okay, so I would say that I'm partway through step 3. So I'll say it again. My step 3 is write out the equations. So, all right, so I've written out the x component of the equation for block 1, and I've also written out the y component of block number 1. Let me scooch down to the bottom half of my paper where I said, let's write out the equations for block number 2. Okay, now I kind of covered it. I don't know if you can see it through here, but there was a force right here. I'll put it just by the green one, a tension, and there was a force right here, a normal, and then here's the gravitational force. Now, we probably need to realize that we've made a tilted axis of 20 degrees because we tried to tilt the axis so that it would be along the incline. And if you come back to the picture, the incline is tilted up at 20 degrees. So you might say something like this. If I took my 2 pens here and kind of had the traditional XY axis, I have now rotated it 20 degrees. So I say that because I'm really curious what this angle is here. Now, this one's a little easier to see. I just rotated up the x-axis 20 degrees. But I'm hoping you'll see that also means I rotated the y-axis over 20 degrees because they started like this and they rotated together. So this angle between the force of gravity and my new y-axis is 20 degrees. Now notice I didn't rotate the force of gravity. I'm still saying the force of gravity is down. And so you might say a negative part of rotating the axis is now my force of gravity is no longer completely in the y-axis. And I agree, that is the negative consequence of rotating our axis. However, that is, that small negative is overcome by the advantage of rotating our axis, which, as I said back here, you'll see that for block 2, that having one acceleration be the full acceleration, one component being the full acceleration, and the other one being 0 has a big, big advantage. So I will live with the unfortunate small disadvantage of tilting. By the way, another advantage, though, is by tilting it, now the normal force is all y. So what I lost for the gravitational force, I gained for the normal force. And I also gained for the tension. So those are two gains and only one loss. And of course, the biggest gain, it still would be this about the acceleration. That's just incredibly powerful. So again, as you write out the equations here in step 3, let me emphasize, try to figure out what direction it's going to move and set up one of your axes. It'll make the equation so much easier, even if some of them have to pay a price. And so the gravitational one pays a price, but the normal and the tension to have an advantage, and the big advantage is the components of the acceleration. All right, so let me see if I can write out the x component for block 2. So remember, we called down the hill positive. And if I can get kind of a component looking thing here, if I take this force of gravity, which I drew in red, and look at its components now, it would have a little piece in the negative y direction and a little piece down the hill, which is the positive x direction. And that's the one I would want right here. And so notice the one down the hill is opposite of the 20. So I would take the magnitude m2g, and I would multiply it by sine of 20 degrees. And that would be a plus. And that's how much force of gravity is down the hill in the x direction. That is this step. Add up all the forces in the x direction, set it equal to mass times acceleration in the x direction. Now, as long as I'm working on this, I might as well do the other side, which says add up all the forces in the y direction and set it equal to mass times acceleration in the y direction. So if you look back here at the force of gravity, this one here would be the y direction, which would be adjacent to the 20 degrees. So I would have an mg, I guess it's m2g, and I would have cosine of 20 degrees. And that would be the negative direction. So again, this is the part that I was saying, that this is the negative consequence of turning. Instead of having all of my force of gravity in the y direction, I now have to have a cosine of 20 degrees. That's still negative, but I have to have a cosine of 20 degrees, which means the other part is in the x direction. Okay, so there is the two components of the force of gravity. The x component, it's down the hill, so that's positive, and the y component, that's into the hill, that's negative. Now, if I look at the other forces, like the normal force is all in the positive y direction, so that would go here, plus n. And if I look at the tension, that's all up the incline, which we're calling the negative x direction, so that would be minus the tension. And that would finish this part where I'm saying add up all the forces. So I've got the three forces. I've got the normal force, which is all in the y, positive y. I got the tension, which is all in the negative x. And then I got the gravitational force, which has a component in the x and a component in the y. But so those are my two columns. There's where I added up my forces in the x direction. Now, what do those have to equal? Well, again, this would be mass of block number 2 times the acceleration. And again, watch this clever trick. The acceleration is the total acceleration. That's the same logic I said that we could do over here for the x direction. It's the total acceleration, and it's positive. That's why I'm saying that A for block number 1 is the same as this A. It's the same magnitude, it's the same direction, it's in the same x. That was the advantage of making each one move in the positive x direction. And then also watch this, the acceleration in the y direction for block number 2 is 0. Again, that was the advantage of tilting our axis, knowing that the block is only going to go down the hill or up the hill, and it won't go into the hill or rise above the hill. And so there is no acceleration in the y direction. And so that's a little easier equation to deal with. Now, you can kind of see what I was saying earlier as we now get to the step 4, the final step, and maybe I'll just review them again, right? It's the 4 steps. Good physical picture, free body diagram, write out the equation. So that's what I just spent most of the time here, writing out the equation. That means setting up an axis for the 2 objects and writing the x and y component for each object. And then finally solve this. And you can see that for the y direction of block number 2, we could get an equation for the normal force, which would be useful if we had friction. And that's why I was saying a little earlier, this one we won't even need to mess with because I don't need the normal force over here to get the acceleration. And that's really what this problem is getting to. This problem is getting to, does it accelerate positive or does it accelerate negative, right? See, this is where we need to kind of interpret our math. I like to use the phrase, read our math. This is the part where it says here, in order for block number 2 to slide down the incline. Okay, so in other words, for it to have a positive acceleration. That's really what that one is saying. And so I'm going to focus my attention then, not on the equations for the y motion, but on the equations for the x motion. And I want this acceleration to be greater than 0. All right, so as I go to step 4 and actually solve this equation, or equations, because I got 2 blocks, I'm going to circle the 2 I'm interested in. I am interested in what is the motion in the x direction for both block 1 and block 2. And of course, they're coupled together. In fact, you could even see here that you can use your mathematics to eliminate one unknown. So let me come over here to page 3 and say, all right, I want to make a greater than 0. So why don't I do this? Why don't I eliminate the tension in here? So why don't I take equation number 1, or the equation for block number 1 in the x direction, and solve it for tension. So this would say M1A plus M1G is the tension. And I'm going to use that and plug it in to here. Okay, so this is going to become, and I think I'm going to need a little more space. So that's why I'm going to go over here to page. I'm going to go M2G sine of 20 degrees minus the tension. Well, the tension, I'm going to use this. So M1A plus M1G equals M2A. All right, so that's what you probably learned in an algebra 2 course, or maybe it's algebra 1, a system of equations. 2 equations, 2 unknowns. And in the process of combining 2 equations, you can eliminate a variable. So I've eliminated t here. And I picked t because I really want what's left in here to be a and the masses, because that's what is given. You want a to be greater than 0. You want to know what tension is needed, what mass is needed, sorry, not tension. What mass is needed in order to make a positive. So I'll keep working here. This would be M2G sine 20 degrees minus M1A minus M1G equals M2A. And noticing that I have like terms, I can move this middle term over to the right-hand side, and they each have an M in them. I'm sorry, they each have an A in them that I can factor out, so I'd have it adding them. And so I would have then left this M2G sine theta 2 minus M1G. Now, if you solve this equation for A, it means you'd have to divide both sides by the sum of the two. Cross that out. And so now I have a combined equation that gives me an answer for what the acceleration is. And so if you were to tell me what M2 and M1 is, now that you've already told me the slope of the incline, I could then tell you what the acceleration is going to be. Now, in this case, we want A to be greater than 0. If they had said something like, what mass do you need to make the acceleration 4 or 5? Well, we can put that in and get that answer. But for ours, we just want it to go down the hill. So we want A greater than 0. So I'm going to put this greater than 0 right here and put in place of what A is equal to. So I would want M2G sine 20 degrees minus M1G over M1 plus M2. And so we want it greater than 0. And so if we begin to solve, we can bring the M1 plus M2 to the other side. And so we would have 0 plus that, so we'd still get 0. We can even factor out a G and divide by G, we'd still get 0. And so we would be left with M2 sine of 20 degrees minus M1 needs to be greater than 0. And we're trying to solve for, let me come back and check, we're trying to solve for M2. So to solve for M2, this says M2 has to be greater than. So I'll bring the M1 over, and then I'll divide by the sine of 20 degrees. So this would work if M2 is greater than, and we were given M1 as 2.9. And so if we divide by sine of 20 degrees, we'll actually finally get a number. All right, so 2.9 divided by sine of 20 and 8.5 should do it. Now you said you played with these figures.
Yeah, that was, it got the 8.6. So
Okay.
that's perfect, yeah.
Good.
That made a lot of sense.
Okay, good. And I hope I wasn't too long-winded. It really wasn't supposed to be that long or that hard, but there's a lot of, I think, techniques you should be shown here of like picking your axes, writing out your equations. And I would encourage you to memorize those 4 steps. Good physical picture, free body diagram, writing out the equation, which includes those 3 steps on how to choose an axis, and then finally solving it.
Right. Well, thank you so much. That was really great.
Oh, hey, well, unless you don't want me to, if I bored you too much, but you want to see the how you could have done this with thinking of it as one object?
Yeah, you can answer the other people's questions first, though. I don't want to keep them waiting.
Well, so I'll get to Shasha. Hang on here. So I will do this then kind of quickly here. But you know what you could do is you could do something like this. You could take block number 2, and you know it's connected to block number 1. And it's kind of, this is the kind of the conceptual part that I'm saying might be kind of harder to visualize. If you kind of imagine kind of straightening out the string, so it looks maybe more one-dimensional to you, And think of this as one object, because remember, these are competing. Remember, block number 1 is being pulled down with M1G. And this one here, block number 2, is getting pulled down the hill by, so we'll have to come back to how we analyze this. So remember, block number 2 is getting pulled down the hill by M2G times the sine of 20. So this would be M2G sine of 20. And if you look at this as kind of fighting with each other back and forth, you would say it would go, in my picture, to the left if M2G sine theta, that's what's pulling it down the hill, if that is greater than this one, which is pulling it up the hill. And then the G's cancel off. And then you can say if M2 is greater than M1 over sine 20, which we calculated to be 8.5. Yay!
I see.
And
yeah.
so thinking of this as one object kind of moving in a straight line would actually lead to a quick answer for this one.
Yeah, definitely a lot less math. That's crazy.
So
Very cool.
all right.
Well, thank you so much.
Good. I
That was
hope
helpful.
that could be helpful. All right.
Great
Right.
day. Bye-bye.
Bye. Take care. All right, Shasha. Let's see. Let's look at yours. You said for exam number 1 was the structure of the test 9 questions instead of 5. No. The tests have always been 5. I think that practice test had 9 questions, maybe even 10, because Don took problems from past tests. I don't even think they were all from the same 2 tests, but it was more than 1 test. He took a bunch of problems from past tests and put them together so he could do that video review. So should we time ourselves based on how many we can do? 5 problems or 9? Okay, so 5 problems.
Gotcha. Okay, yeah, that clears it up. Thank you.
Yeah. He just he put together that review years ago because he just wanted to do more than 5, but hopefully he didn't want to. But he certainly didn't want to mislead anybody to think the test was as long as 9. So it's 5 questions. Giving you, I think you were asking this morning. That'll take 25 minutes per problem. So if you do the ones as I was saying. That are easier for you, you can read them and they click, then boom, jump on those and you'll do those under 25 minutes. And then the ones you're having, a little more difficulty, you won't feel quite so pressured to meet the 25 minutes because you're kind of ahead of the game already.
Already. Yeah. I've already kind of started on the packet and yeah, I'm just going through it today.
Good. Yeah, that's what you said you were going to do. So good. Yeah. And same advice I gave you before. Do that practice one. It's a great one. And again, know that there's only 5.
Sasha, are you in the Discord for this class?
I believe I am, yeah.
Okay, yeah, because some people were talking about like the testing format who had Young for 121.
Oh, okay. I haven't really been looking at it. So
it's
people were
helpful.
asking about the same thing.
Yeah, it's helpful. Some of us are gonna like study together Monday.
Okay, cool.
So yeah, you can it's in the general chat, you'll see it.
All right, yeah, I'll probably join that then.
So here's there's a link if you don't have it.
Thanks.
You got it, man. Dr. Young, I have a question for you. If we have time, we're kind of
sure.
Okay, we're kind of closing on the end of it here. It's from homework.
That's okay. I don't want to leave you guys struggling.
Yeah, it's from chapter 28 homework, problem 45, problem 45.
chapter, 28, number 45.
Yes, sir.
Okay, that's right. You've been working ahead. I'll swing over to that. And just in case there's a question about.
I don't mind if you take, this is not, obviously not like pressing for the exam. So
No, well, I'll take it. Let's see how long it is, and I'll help you through it here. I have to. I had a problem with my computer. I had to reboot this one. So let me call that back up. Let's see. Where is your class? 122. Let me call up your homework again. Homework. And then I'll go all the way down to chapter 28. And let me even index it here. What time is it? 4:26. So that maybe somebody next week might want it. And maybe somebody this week, who knows? 45. So it says a rechargeable battery has a constant EMF of 13.2 and an internal resistance of, okay, so chapter 28, number 45. And I like to draw my batteries kind of like this, put a little knob on the end and say, okay, this is plus. So there is this voltage inside, which is 13.2. And by the way, that's the number for a car battery. So I'm sure they're talking about here your kind of 6-cell lead acid battery. And then there's some internal resistance. So you're going to lose a little bit of voltage trying to get out of the battery. That's why we often call car batteries 12 volts, because the workable, or what we call the terminal voltage, is usually around 12, because the voltage from the chemical reaction, the 13.2, has to migrate through the acid and the plates, and then that internal resistance loses some of our voltage. And so the actual voltage you get on the terminals is going to be under 13.2. And how much under would be what we call the IR losses, the Ohm's law. Now, that might be related to the question. I better keep going and read the question. It is being charged by a 14. Hard to read that number. Is that 14.7?
it is a 14.7. Yeah.
Yeah.
Kind of cuts
Okay.
off.
So again, these are pretty realistic numbers, because your car's generator is usually set around 14.7. Of course, you have internal resistance. So if you have like a dashboard on your car, you'll see that it kind of runs a charging of about 14.3, 14.4. Because there's some internal resistance. This problem doesn't say to worry about any internal resistance of our generator. So we'll pretend there is no internal resistance in our generator here. But it's saying it supplies this for 1.8 hours. After charging, the battery returns to its original state. Oh yeah, this gets a little involved as it delivers the current load. Let me, you know what?
So
Go ahead.
I hate to tantalize you.
Yeah.
Numerical problem, but I worked it out.
Good.
I got it wrong. I looked at the solution, back and forth. But I worked it all out, and I'm struggling with the conceptual aspect. So when we calculate the incoming current, we subtract the voltage of the battery from the voltage of the power supply, and we end up with a I'm seeing 1.5, but I feel like it should be. I wrote down 1.5. Oh yeah, we do end up. Sorry, yeah, we end up with a 1.5 volt difference. But then, way towards the end of the problem, so that gives us the current, right? Because we know the resistance. And then way towards the end, we want to know the power that the power supply supplied, and we multiply, we have power times time, which ends up, we describe power as current times voltage of the power supply
Mhm.
times the time elapsed. And it feels weird that we're using the full 14.7 volt difference there instead of the 1.5. But then I see that the current is showing up in the equation, which does feel like it's accounting for so.
Okay.
I don't know. Maybe I just have to think about it more.
Okay, well, let me help. Okay, good. I like what you said. Let me help you a little bit, and then maybe I better address the question related to the test. But here's what I'm going to say to you. The efficiency is defined, and they list it. But let me do this for a moment. Let me just point out that if you did your first series of equations, you would go something like this. If you're charging it, you would go plus 14.7. So here's the Kirchhoff law. Then as you run the current backwards in the battery, that's why you're charging it, okay? There would be minus the current, okay, times the resistance, then minus the 13.2, and that would equal to 0. Okay, and so with a little bit of math, and I'll pause on doing the math, but that would tell you the current that is used to charge it. Okay, so knowing that number, read carefully here what they mean by the efficiency. And I guess I also need to see how long we've been charging. It says, after the charged battery returns to its original state, as it delivers a constant current to a load resistor for 7.3 hours, find the efficiency of the battery as an energy storage device. That is, here it is. The efficiency here is defined as the energy delivered to the load during the discharge process, divided by the energy delivered by the power supply. Okay, so let me start with that. Energy that we put from our power supply into our battery.
That's where I'm hung up. Yeah.
Okay, so I'm going to say that if you take power and multiply it by time, you get energy. So the power is the current times the voltage. And if I multiply that by time, I will get the energy. Now, here's where I think part of your conceptual challenge is coming. While we were charging it, we just did this current. And let me call it current during charging, okay? And if we're talking about the power coming from our power source, then we would do the 14.7, but not the 13.2. This is what's being delivered to the chemical reaction in the battery. But our power is being delivered to both the chemicals in the battery and this heat. And so while we are charging up the battery, the energy we're delivering, some goes to being stored in the chemical reaction, but some goes to heat. Like if you ever felt your cell phone, while you're charging it, it can get pretty warm. And so the energy actually being delivered to your phone is part charging the battery and part making heat. Not that it wanted to make heat, but just because of the nature of the electronics, we have to.
Entropy.
Yeah. So we sadly have the reality of physics. And so if we can reduce that heat, we would have more efficiency. Okay. So
my hang up is with the voltage. It's like, because it feels like it should be the potential difference between, like, it feels like it should be 1.5 volts, 14.7 minus 13.2. Because, like, then if I had a battery that was like 130.2 and, I scaled up then I would just have like way more power, but do you know what I mean? Like if I had like a million volts and like 999,999 volts, then it would be, am I way off there? I guess yeah.
Okay, let me try this. The difference, okay? The difference in voltage would be what you would want if you said, how much energy from what I delivered did not go into the chemical reaction, it went into heat. See, that's what the difference is. The difference is how much did I deliver not go into the chemical reaction? It went to heat.
Well, I'm thinking, okay, maybe I'm getting mixed up because like I'm not thinking about the resistor. I'm just thinking about the voltage of the battery pushing back, and
Okay.
then the relative potential difference between the like. But I think that's accounted for in the current, and I'm just not seeing how it all connects together. Maybe I'm not articulating it very well, but
I'm going to try a water analogy with you.
okay.
Okay. And, I'm going to go back to this reservoir that we talked about and a couple of other times. And that reservoir is the push. That's the voltage. And I'm going to connect it to something. And I'll change my analogy a little bit. Maybe I shouldn't have made my tank so high. Let me cross this out on the top. Because the analogies I was giving you before was like this big tank and we would just fill it up until it stopped filling. But here, if I'm charging something that has a capacity that can only go to 13.2, yet I'm pushing it with water that has a height of 14.7. As I go to fill up this tank, the energy I deliver gets stored in the tank at a height of 13.2. Anything above that falls off and rubs, or maybe it doesn't go as high as it should because there's rubbing inside here. And so the difference between these heights of water is the energy lost between what I have to work with and what I'm trying to store. So the difference in these, and that's what you're tempted to put, the difference in that is what is going as wasted energy. It's going as heat. It's not going into your storage.
Well, I don't know. That doesn't,
Or how about this for a second?
Because okay, yeah.
How about mathematically I do this? There is the principle of conservation of energy.
I do, yeah.
So if I say energy total, and I'll say that total is the energy delivered by this power supply, must equal to the energy that goes into storing in this battery I'm trying to charge, plus the energy that goes into heat that sadly was a necessity to charge this battery. See, this energy total, I'm trying to say, would be the current times the voltage multiplied by time. And I'm trying to say that would be the same as, you let me kind of break this into its two pieces. The storing energy and the heater would have the same currents. We would do them for the same time. And this would be the 13.2, and then this would be the delta V. So this is the energy going into storing of the battery. This then, the delta V, the difference between the 14.7 and the 13.2. This delta V is the energy going into the heat. these two energies together add up to the energy that's being delivered by your battery. So again, if you wanted to know your charging battery, you wanted to know, I shouldn't call it charging battery, this one, the 14.7. So if you wanted to know the energy that the 14.71 is delivering, then you take its voltage. If you want to know how much goes into storage, because you're charging up this battery, you would do the voltage of the charging battery. And if you want to know how much goes into heat, you would do the voltage on the internal resistor, which would be the difference between those two.
Okay. Really? No, really. Thank you for holding my hand through that.
So I guess another way of saying this is the delta V is, as you said, the voltage between these two.
Yeah,
So,
I think what was bothering me was I was feeling like the battery wasn't pushing back, with its 13.2 volts, and it felt like the power supply was just getting a free ride to dump all that 14.7 in, and it felt like I should be subtracting off the pushback from the battery. But just watching you work it out, and it's the current would be decreased when you subtract the voltage in the first step.
but again, maybe I had a hillside that was 14.7 meters up with water running in it. And I'm trying to fill up a tank here that is 13.2. You're right in the sense that this is pushing back. That's why the rate at which water goes through here would not be as much as if this was lower. And so the lower this voltage is, the faster this rate is, but the loss is connected to the friction of this water going down. And so the difference in height does contribute to, as you said, how much flow. And how much flow isn't giving it a free ride. Maybe that's the thing. You're not getting a free ride. You as you ride through here, you get more water going through here, but because of the resistance, you lose that energy. There is this bumping and rubbing and heat created. And so the more water you get through here, the hotter this thing gets. Now, granted, you might say, well, if you made this up here 14.7, you would lose no energy. And I would say, okay, fair enough, but you would also have no flow. So, you're not losing anything, you're not flowing anything.
Noted.
Which is why, again, when your battery is low, if you've ever had your cell phone low on charge, like at 20%, the voltage is way down. And when you first plug it in, man, that current just rips through there and it gets hot. And so you plug in your cell phone at 20%, and it doesn't take long when you come back and you can feel it. It's hot, but more than that, it's no longer at 20%, it's gone up to 60%.
Yeah.
But now, and actually 80%, it gets charged back to 80% pretty quick because there's a huge difference. But once you get to 80%, that difference, back here, that difference is very little. And so the rate at which it's charging is really slow. So it takes a long time to go from 80% to 100%, and it doesn't get hot on you. So
I like that little physical example. Those help. Yeah.
Okay.
So I'll let you, sure. Rhythm win, of course.
Yeah. And so, and actually, that's the good thing of batteries, really, because really, if you wanted to use it right away, you could plug it in at 20 and get up to 80 and then take it, And 80% is pretty good charge. So you're like, okay, I'll survive at 80%. But if you really want to get 100%, you just, you're going to wait a long time. And so it's probably best to do that overnight. All right, those are good ones. After the first test here, we'll have some more discussions on these.
Okay, cool. Good.
All right, hey, let me jump back here. I saw. Oh, Rhytham, right? Not saying your name right, I'm sure, but Rhytham, yeah, did you have a question for me, or you just kind of
Yeah,
checking
I
in?
had a question. It's rhythm.
Rhythm? Oh, yeah, of course it is. Okay.
So this one is part of our weekly quiz. That's due tonight, but it's getting kind of late in the day, so I'm sure most people have taken it already. From 121.
Okay.
So I was a little pressed for time. Again, it's 20 minutes, and I got the last one wrong, and still a little unsure of how to complete the problem. So I was just hoping to maybe it doesn't seem like it's that long at all. Seems like it could be a pretty short one. So
All right. Yeah, let me hear it.
okay, so it says, let's see.
Maybe I'll draw it while you
So it says
about
a grocery store employee pushes 3 nested shopping carts through a parking lot.
Okay. So hang on, I'm gonna draw 3 shopping carts and it's being pushed. Okay.
And they're supposed to be connected.
Okay.
Yeah. And then there's no friction.
No friction. Okay.
Each cart has a mass of 20 kilograms.
Okay.
And then it says the employee pushes on the handle of cart number 1 with a horizontal force of 184 newtons.
Okay.
And then the question is, the force exerted by cart 1 on cart 2 is blank newtons. And it does say a little hint. It says, hint, first calculate the acceleration of the whole system.
Okay. Yes.
So, yeah.
Yes. Okay. And I'll begin with maybe a good piece of information. I don't know if you caught this in Newton's theory. It's easy for beginning students to miss this important detail. Okay.
Mm-hmm.
And I'm going to use this important detail to answer this one. When we say add up all the forces and set it equal to MA, we're really saying add up all the exterior forces.
Right. Okay. Yeah.
Okay.
I do remember that. So like Newton's laws don't apply to forces that are interior to the system, right? Or not that they don't apply, but when you're summing all the forces, it's exterior, right? Like,
yeah, I would say this way. If you had an object and they're connected in some way,
mm-hmm.
because of Newton's third law, you split it in half, one pushes and one pulls, and they're equal and opposite. So when you do include the internal ones, they always come out to be 0.
Right. Okay, that makes sense.
Okay, so what that means then is that for a particular problem, the good news is we don't have to worry about internal forces. The bad news is if we wanted to solve a problem and the force was internal, we can't get it through Newton's laws. It cancels off. Okay, so keep that in mind, because here's a little trick that the hint is trying to say.
Okay.
The hint is trying to say this, that if you treat all 3 of them as your system, and you label them 1, 2, and 3, the forces between 1 and 2 and between 2 and 3 are internal, and you don't have to worry about them. But also keep in mind, you can't solve for them.
Right. Okay.
So when the problem says there's an external push coming from an employee who pushes it with 184 newtons, and it says add up all the forces and set it equal to MA, thinking it as one giant object, then the only force I have to worry about is the 184. I don't have to worry about the force between 1 and 2 or the forces between 2 and 3. Those are internal. So that's the good news. Now, when it comes to the mass, it would be the 3 of them. So that would give me a mass of 60. And this is the part of the hint that says, do the acceleration first. All right. So I would then take my calculator and go 184 divided by 60, and I get a hair over 3. So 3.07 meters per second squared would be the acceleration. All right, now watch this. Here's where I'm going to take advantage of what you just said, that good news, I don't have to worry about internal forces. Bad news, I can't solve for them. And this problem is ultimately asking for the force between 1 and 2. And as long as I think of all 3 of them as a collective group, I can't do it. But watch this.
Right.
What if I think of 2 and 3 as a collective group?
Aha.
Now the force between 1 and 2 is external, and the force from the employee isn't even touching 2 and 3.
Right. Okay. So when you do, like, let's say you drew a free body diagram for 2 and 3, you wouldn't even include the 184.
Right.
Right.
I would only include, that's why I tried to do it here in green. I would
Yeah.
only include the force between 1 and 2, which is what we're looking for.
Okay.
And now these 2 carts, the mass would only add up to 40. And the acceleration would still be the same as the collective group,
Mhm.
3.07. And that's taking advantage of these internal ones. So times 40 would give me, it's like 123.
Okay. Yeah. And I'm pretty sure that because it gives you the right answer afterwards. Yeah, that was definitely the right answer. Okay. Yeah. That's definitely a nice little trick to just treat all of them as a system and then break them up so you can, yeah, that makes
Yeah.
sense.
And so the bigger picture I'm trying to get across here is that concept of internal forces. Internal forces have their goods and their bad. The good, if you don't have to worry about them. The bad is you can't solve for them. So you might have to change your viewpoint in order to make it an external force. And that was the technique. Yeah.
Okay. So in general, if there's like ever another problem or situation where things are like connected, not necessarily like internal forces, like, I don't know, atoms and that kind of stuff, but if they're like carts connected or certain blocks that are connected, can you generally, think of it as like all of them and then 2 and then 1, you know what I mean?
Yeah, let me give you a kind of a classic problem.
Okay.
Classic problem is to build a ladder. And a ladder usually has like a top part for it to hinge out, and then a connecting piece. Okay. And maybe somebody stands on the ladder partway up. And the question asks, what is the tension in this connecting rod between them? Well, so long as you think of the ladder as one big object. Whoops, I didn't want to include the human, sorry. As long as you think of the ladder as one big object, you can never solve for the tension between them.
Right. And that's because it's internal to the system you're considering. Okay.
The same logic. So the key to a problem like this, and it's the same as those shopping cart, is at some point in the problem, we need to look at just half the ladder. And so that way this piece, and for that matter, this piece which we don't include when we look at the whole ladder, have to be included.
Okay. Yeah, that's a nifty little trick right there.
And then, of course, like the one you just saw, you probably want to do the whole ladder at first, because when you do the whole ladder, you can get an easier solution to what the normal force is, because then when you do half the ladder, you are going to need that force down there. And so you do need to first think of the whole ladder in order to figure out that number. And well, and maybe I should point out the obvious, hopefully, that the other external force is the weight of the human on it. So
Yeah.
whole ladder or half ladder, that's an external force. But as I split the ladder in half now, I would have the force from the human, the force from this contact with the ground, which I figured out by looking at the whole ladder.
Would the normal force be the exact same number, or would it be half? It would be the same, right?
It only comes out, and we're probably getting a little bit ahead of ourselves, to be exactly the same number if the weight is evenly distributed.
Yeah, that makes sense.
So if there is either no human on it or the human's on the top piece, then the weights are equally distributed.
Okay, yeah, that makes sense, because that conceptually definitely makes sense now.
Yeah. And so to figure that out, we got to wait till we do torques and rotation. So we're going to see a lot more of this in chapter 12.
Cool. All right. Well, thank you. Appreciate it.
Okay.
Yeah. All right. Have a good one.
All right. Take care. All right. Well, hopefully those were all helpful. Sasha, keep studying, and we will answer anything you get. I'll do it either by video or special Zoom, but I think you're doing well. Keep working.